So, where are we at here? The first thing tonight is I got your homework to get back to you. Rob's got yours in Johnson City. I already emailed the others back. It's homework 3. And that's going to be for Tuesday. And Tuesday's the 24th. And so this is just chapter 3, right? Where we're looking at these normal distributions. I'm interested in areas under curve. So I only picked 4 problems this time. That one there was multiple choice. 3/16 is multiple choice, so there's 3 problems where you got to work things out. Can I give a couple comments about these? You notice I'm not writing any graphs. You're going to use Minitab. These are these normal distribution calculations. 3.26 on page 95. What they're doing is they're talking to you about two different groups that have the same variable measured on it, and this one has a normal distribution of mean and standard deviation, and this one has a normal distribution of mean standard deviation. And they want you to use the 68, 95, 99.7 rule to tell me what values that 95% is between. Now you notice, anytime I say 95, you see me put up 2 fingers because that's 2 on either side, 99 points. So you're going to use the 95 part of that rule. That's what they want you to use in 326, and the problem tells you that. And then in 330, look, I was looking for problems that gave us all the types. I needed one that used the 68, 95, 99.7 rule. I need one where you go to the left, go to the right, in between, and that's 3.30. And there they're talking about fruit flies. It turns out the length of the floor of the thorax, where the wings and legs attach, and the population of male fruit flies is approximately normal with a mean of 0.8 millimeters and a standard deviation of 0.078. So instead of looking at monsoon rains or whatever we looked at on Tuesday, now you're looking at the length of the thorax of a male fruit fly. You got a normal distribution, and then part A, B, and C. Part A, you're looking to the left. Part B, you're looking to the right. And part C, you're looking between. And then the 337 is you're trying to find the values of the quartiles, the first quartile and the third quartile. Remember, that's a problem where you work backwards. Right? Because if we're telling you the first quartile, we know there's 25% of the area to its left. If you're looking at the third quartile, there is 75% to its left. So by it asking you for the quartiles, it is giving you the percentages. Okay? Now, I usually announce tests a week ahead of time. But our first test, for some reason, I'm ahead of schedule here on my thinking. It's going to be on Tuesday, the 29th. Okay? And what I'm thinking about at this moment is chapters 1 through 6. We'll see what happens when we get to next week, but that's what I'm thinking at the moment. Right? It's going to be 40 questions. It'll be multiple choice. It'll be A, B, C, and D. I don't do all the above or none of the above. The answer's actually sitting there looking at you. Right? We'll have more of a talk about this probably next Thursday, but I just wanted to let you know where I'm at, right? So you got that homework. I mean, I know I want to have the test on the 29th, and that's the chapters I'd like to have it over. Okay? Now, one more thing about chapter 3. And it's really about table A. Remember, table A was the table in the back of the book, or you printed it out, where we looked up all those areas to the left of a particular z-score, correct? Here's my thought about table A. If for some reason, I don't think it's going to happen in these problems you're doing, but in the future, it's possible that you get a z-score that doesn't fit the table. And what I mean by that is, it's possible that you get a z-score that is bigger than 3.49. The largest z-score you can look up on the table is 3.49. And I have a bad habit later in the semester of assigning problems where the z-score is bigger than that. If that's the case, what we assume is, remember, the table always tells me the area to the left. So the area to the left is approximately, everybody understand my little squiggly lines? That means approximately. Is it exactly 1? No. Is it close enough for 1 to say it's 1 for us? Yeah. Now, if the area to the left is approximately 1, then what is the area to the right? Almost 0. Right? And then the larger it gets, the closer it is to 1 on the left, and the closer it is to 0 to the right. So that's if you get a z-score of 5.27. Okay, I got a z-score of 5.27. Well, shit, the area to the left is approximately 1, the area to the right is approximately 0. Now, what about going the other way? If I've got a z-score and it turns out to be smaller than minus 3.49, because if you look at your table, the smallest z-score you can look up is minus 3.49. Well, this is just the opposite. Then the area to the left is approximately 0. Exactly 0? No. 0 to 4 decimal places? Yeah. And that means the area to the right is approximately 1. So that we can handle any z-score we're given. If you're between minus 3.49 and 3.49, the table works. If you're bigger than 3.49, that's what you do. If you're smaller than minus 3.49, that's what you do. Okay? That was the last thing I could think about that I hadn't mentioned on Tuesday about the table. Okay, that'll save us some emails later. You know, all of a sudden you get a z-score of 10.25 and you're going, I'd like to give those problems to you because you'll freak out. All semester, all my z-scores has been they fit the table, and all of a sudden you give me a problem and the z-score turns out to be 10.25. What does that mean? Well, that means that observation you're looking at is 10.25 standard deviations greater than the mean. That means the area to the left is almost 1 and the area to the right is almost 0. Right? You're a long way away from the center when you're 10.25. Okay? Now, here's my next thought. Now we're ready to start chapter 4. Right? That gets me cleared up with table A, tells us how to fix those problems. Here's the way I think about this. All right? The first 3 chapters all went together. It was graphs, it was calculations, and then we summarized everything with the density curve, and then we started looking at those normal curves and finding areas, which was proportions, which are percentages. What makes the first 3 chapters all go together is we had a set of individuals, and we had one variable, and we told everything we could tell about its distribution. Right? We only looked at one variable at a time. Okay? Whether it was monsoon rains or whether it was the length of the thorax of a fruit fly or wherever it was back there. And, you know, all this stuff in chapters 2 and 3, you understand we were looking at a quantitative variable, right? Anytime you're going to start calculating stuff, you're looking at a quantitative variable. Categorical, it was real simple, and we were done with it in chapter 1. Somebody give me a table or a list of categories and give me the percentage or count, you're done. Everything we did in the first 3 chapters was about the distribution of a single variable. I mean, I got histograms, stem plots, bar graphs, pie charts, box plots, mean and standard deviation, 5-number summary, IQR, the 1.5 times IQR rule, and then all that stuff in chapter 3. We were still looking at a single variable, right, measured on some set of individuals. Yes? Okay. So now 4, 5, and 6 go together. Well, if we've taken care of looking at a single variable by itself, what are we going to do in 4, 5, and 6? You're going to look at 2 variables at a time. You're going to have a set of individuals, and you're going to have 2 variables. Right? So, here's what we do now. You know, before it took a chapter for graphs, and it took a chapter to calculate center and spread and everything, right? Not this time. Chapter 4, the title of it is Scatterplots. That's our graph here. And correlation. That's going to be the calculation we look at here. Now, the way we think about chapter 4, 5, and 6, we are looking at the relationship between two variables. Okay. I use relationship and I interchange a word with you on you here. Sometimes you'll hear me with the association between the two variables, the relationship between the two variables. Now, here's the deal. Chapter 4 and 5, we're looking at two quantitative variables. In Chapter 6, what's left? Let's look at two quantitative variables. Let me ask you this for a second. I just want to see if you follow anything I ever say. Have we talked about the relationship between two variables before? Maybe where you had a categorical variable and a quantitative variable. Maybe you had the same quantitative variable measured on two or more groups. Maybe you had how much people tipped depending on the odor in the restaurant, whether it was lavender, lemon, or no odor. Was we looking at two variables there at a time? Yeah, it don't sound like that back in Chapter 2, but you did. Right? You had the same quantitative variable measured on three groups there. Right? That was a categorical and a quantitative. Now, it's either two quantitative or two categorical, and that's Chapter 6. Okay? Now, I got to make one statement here, and it seems like an obvious statement. If we're going to deal with two variables, obviously, you measure both variables on the same individuals. Maybe it's not obvious. See, I'm going to look and see if there's a relationship between two variables. It makes no sense for me to measure your heights and their weights and start talking about the relationship between heights and weights. They're not on the same set of individuals, right? So what's going to happen is you're going to have a set of individuals, yes? I'm telling you about your data set. You're going to have a set of individuals, and you're going to have two variables measured on them. So you'll have, for that individual, you'll have two values, right? One for that variable and one for that one. Okay? Now, here's the way our book starts. I'm on page 101. I'm going to read to you a little bit here. It says, a medical study finds that short women are more likely to have heart attacks than women of average height, whereas tall women have fewest heart attacks. Okay. Are they trying to tell you that there's a relationship between a woman's height and her risk of heart attack? Yeah? Shorter women have a higher risk, taller women have a lower risk. Yeah? Let's read the next one. An insurance group reports that heavier cars have fewer deaths per 10,000 vehicles than do lighter cars. Now, that's a shock. What are they telling you? Something about the weight of the vehicle has something to do with the number of deaths in that particular vehicle. Yes? Is there a third one? No. Can I go back to the one about the woman's height and her risk of heart attack? Or, the number of heart attacks the women had depending on their different heights? Can we go back to that one for a second? So what happens here in these chapters is you've got to be careful. Because we picked out two variables out of many that we could have talked about, and we want to talk about the relationship between these two. Yes? Like somebody wanted to talk about the relationship between a woman's height and her risk of heart attack. Are there some things we're missing here? Do you really think that a woman's height has something to do with her risk of heart attack? I mean, my man over here, he's shaking his head no fast. He's like, dude, what are you talking? No, that was a medical study. You understand, right? What happens is people pick out two variables and they want to talk about the relationship. Well, what I would like to point out to you is there's some other ones we might have, should have thought about. Like diet. Nothing personal, ladies. Exercise. Do you think that maybe a lady's diet, maybe her exercise might have something to say about it too? I mean, I would have wrote weight, but the ladies would have just killed me. Right? So here's the thing is, again, we pick out two and we want to talk about those two. But there's these other variables that like they've just ignored. right? We didn't even think about those. These have a name. These are called lurking variables. That we picked out two to talk about the relationship between them, and all of a sudden, if we stopped and thought about some other variables, it might be these over here that's causing what you're seeing here. We have to worry about this through these chapters. You have to worry about this idea. The reason they're called lurking variables, they're like lurking in the background, right? We just picked out two, and then I got these other ones hanging out over here that might have something to do with what you're seeing here, right? Now, we're going to talk more about that in Chapter 5, okay? But I want to bring this up that, look, when I'm looking at taking a bunch of women, and I want to talk about their height and their risk of heart attack, I could have measured their diet, what they eat. I could have measured how much they exercise. I could have measured their weight. I could have measured how many times they went to the doctor in a year. All these variables from there down, right, those are lurking variables, and they may have something to say about this relationship you're seeing here between a woman's height and her risk of heart attack, okay? That we just picked out two, but there's other ones we should have, might have thought a little bit about, okay? I just wanted to get that out there to you that we're not done with that thought. Okay? We have to be worried about the ones we didn't pay attention to. Did they have some kind of influence on what we're looking at? Now, since we're dealing with two variables here, we need to talk about what's called an explanatory variable and a response variable. See, here's the thing. Sometimes the variables play different roles. Okay? When we see the variables that we're looking at, the two we're looking at, and they play different roles, we're going to name them. We're going to name one the explanatory, and we're going to name the other a response. Okay? And so if I flip to page 102, on the top of the page, there's a little box there that's going to give you these definitions. And then I'm going to add a little bit to these. It says, a response variable measures an outcome of a study. Look, it's a response variable. It's a response to something. It's a response after the fact. An explanatory variable may explain or influences changes in a response. Okay, so here's the way I think about it. If you're thinking that one variable explains or influences the other, then the variable that is doing the explaining or the influencing is your explanatory variable. The variable that is being explained or being influenced is your response variable. Okay? So you want to go back to the women's heights and the risk of heart attack? There they're trying to get you to think that the women's of height helps explain the risk of heart attack. The women's height is the explanatory variable. The risk of heart attack is the response. Now look, let me give you my example. It's an example in the book, but this one always sticks with me. Let's say I want to know how the number of beers you drink, does that influence your blood alcohol level? I give you something all college students are supposed to know about. Right? Do the number of beers you drink help explain your blood alcohol level? Does it? And if you don't know this, you should. You do understand the more beers you drink, the higher your blood alcohol level. And if you don't understand that, the little cop that pulls you over and gives you the little test, he'll explain that to you. Okay? We're treating the number of beers that you drink as your explanatory variable because we're thinking it explains or influences your blood alcohol level, which will be your response. Okay? So, look, this is the deal. This is one way that I will call one an explanatory and the other a response variable. When I think one of them explains or influences the other, the one that is doing the explaining or the influence is the explanatory variable. The one that is being explained or being influenced is going to be your response variable. Now, can we take a look at example 4.2? It says a college student aid officer looks at the findings of the National Student Loan Survey. She notes data on the amount of debt of recent graduates, their current income, and how stressed they feel about college debt. She isn't interested in predictions, but she's simply trying to understand the situation of recent college graduates. The distinction between explanatory and response variables does not apply. Look, if you just got two variables and you're interested in see if there's a relationship or not, I don't think one explains or influences the other. Hell, I just got two variables, right? I'm not going to call one of them something and the other one something. I just got two, all right? Now, before I read the rest of that, in this class, that little distinction between explanatory and response shows up two different ways. One explains or influences the other. That's one. We might want to use one variable to predict the other variable. Actually, we like to do this a lot in this class, in this next chapter. So you've got two variables, right? So you would like to use the value of one of the variables to predict the value of the other variable. Like I might want to use, I'm going back to that example. I might want to use a student's amount of debt to predict how they feel about college. Right? As soon as you see the words predict, you want to use one variable's value, right? I just say variable. One variable's value to predict the value of the other. You have to make the distinction between explanatory and response. Not one explaining or influencing the other. I'm using one to predict the other. You see this variable right here? This will be your explanatory variable. This will be your response. The variable that you're using to make the prediction is your explanatory variable. The variable that is being predicted will be your response. That's a necessity when I want to do prediction using one variable's value to predict the other. One of them needs to be called the explanatory and the other one needs to be called the response. Look, eventually in this class, what we want to do with all this, that's my two ways that this shows up. One explains or influences the other. One predicts the other. We use one to predict the other. See, like what we'd like to do in this with this explanatory and response situation in a lot of studies is we like to start making changes in your explanatory variable to see if that causes a change in your response. What am I asking you then? I'm asking you, does this one have an influence over, does the explanatory variable have an influence over the response? You want to think about this, making changes here, does it cause changes here? Do you think if I change the number of beers you drink that I will change your blood alcohol level? And the answer is yeah. That's the reason your book gives you that as the first example here. We think that one explains or influences that one. We know if we start making changes in the explanatory variable, that'll cause a change in the response. That's what we're looking for here, right? See, that all goes with me thinking that one influences the other. And then this other one is about prediction. Now, I'm going to give you a little strategy here because I gave you a strategy with chapters 1 and 2 and so on. So, my strategy for trying to, I don't know, I was thinking about this last night. You know, all that stuff we did in the first 3 chapters, that's like exploring the data, right? That's like data analysis. I try to stay away from those fancy statistical terms. We explored the data, right? You were trying to tell me about the distribution. And I gave you a strategy for doing that. You know, make a graph, add numerical summaries. Can we summarize the pattern? Talk about outliers, things like that. We want to do the same thing here, right? And what I'm talking about is not a distribution. Now you're looking at a relationship between 2 variables. So the first part of the strategy is plot that's the way everything works out in this book. Plot your data. Now, I didn't give you the graph yet, but I'm going to in a moment. And then, what are you going to look for? You're going to look for an overall pattern. Striking deviations. When we did this before, we did it with a histogram or a stem plot. And the overall pattern was, you gave me the shape, you gave me the center, and you gave me the spread, right? And then the striking deviations were your outliers, the ones that didn't fit that overall pattern. We're going to play the same kind of game here. And then number 2, numerical summaries. You know, we calculated center and spread. We had a formula to figure out if you had any outliers in the data. We have different numerical summaries here. So we're playing the same game over again. Make a graph. Tell me what you see. Let's do some calculations. Now, there's only one graph this time. Okay? So when you think about picturing or displaying relationships, or if you like, associations, our graph is called a scatterplot. There's only one. That's the one we always use to display relationships. Now, here's the catch. You got to have 2 quantitative variables. This will not work for categorical. So a scatterplot is going to display or show you, give you a picture of the relationship between 2 quantitative variables. Now, here's what I would like to do. I want to look at example 4.3. I want to show you if we were going to make it by hand, this is what we would do. Then I'll show you how we're going to make our scatter plots. Okay? It says figure 1.8 on page 27 reminded us that in some states, most high school graduates take the SAT. I don't know. That was in chapter 1, right? There was I'm thinking there was a histogram or something back there. To test the readiness for college. And in other states, most take the ACT. Yeah, that was definitely back in chapter 1 where I had the 2 groups from the same histogram. Who takes the test may influence, anybody see the word influence there? The average score. Let's follow the 4-step process to attack this problem. Look, we want to look at this SAT score stuff. It says the percent of high school students who take the SAT varies from state to state, obviously. Does this fact help explain differences among the states in average SAT math score? Now, here's what I'm going to do for you. Your individuals here. Look, I know we're all the way in chapter 4. That takes you back to the beginning. Our individuals here, I'm assuming there's just the 50 states. I don't believe they threw in the District of Columbia. They might have. If I could find the table for you in the book, I'd know for sure. Give me a couple minutes and we'll figure out. I don't know if there's 50 or 51. Okay? The 2 variables you have measured on them is the percent taking, the SAT, and the state's average, what is it, the math part? Average SAT math score. Now, these are both definitely quantitative variables. Now, I'm going to read one thing to you again. The percent of high school students who take the SAT varies from state to state. Does this fact help explain differences among the states in average SAT math score? Which variable is trying to influence the other? The percent taking. The other one must be the state's average SAT math score. This is your explanatory. This is your response. And I'm getting that right. I mean, I'm not reading the rest of it. I'm picking this to see. I see the word influence. All right. Well, the percent taking the SAT, they're wanting to know, does that have an influence on the state's average SAT math score? Percent taking must be your explanatory. State's average SAT math score must be your response there, because I see that word influence, or it helps explain. Okay? It says, examine the relationship between percent taking the SAT and the state mean score on the math part of the SAT. Choose the explanatory and response variables. Make a scatter plot to show the relationship between the variables, and then we'll interpret the plot to understand the relationship. That's okay. We're still working on making the plot. It says, we suspect that percent taking will help explain. I don't know. I saw influence, and now percent taking is helping to explain the state's. That's the reason for explanatory and response, the way we have them laid out, right? It says, we want to see how mean score changes when percent taking changes. So we put percent taking, the explanatory variable, on the horizontal. If it's on the horizontal, then the other one, the state's average SAT math score, goes on the vertical or the Y. Look, here's the deal. When I start making a scatter plot, there's an X and there is a Y. If you have made the distinction between the explanatory and response variable, like one influences the other, explains the other, or you're using one to predict the other, the explanatory variable always goes on the X, and the response always goes on the Y. If you just have two variables and you didn't make that distinction, put one on the X and the other one on the Y, nobody cares. But if you've made the distinction, explanatory and response, explanatory goes on the X. So what was the explanatory variable here? I'm just going to write it as percent taking. That means on the Y must go the average SAT math score. Now look, I'm assuming you got it here that the percent taking is going to go from 0 to 100. Right? They could have nobody take it, or they could have all the high school students take it. And then I'm going to look at their little graph here, and you notice it looks like they start with a score of 450 is the lowest SAT, average SAT math score for a state. And then what do they go by? It's 25, 450, 475, 500, 5 1/4, 550, 575, 600. How far I got to go? 6 1/4. Okay. Now, I'm going to use what they're telling me here. They got one state for us. The rest of the table, you know, there should be a table with all the states and both variables. They tell me that Colorado they tell me that's one of my individuals in my data set, and they tell me that they got 14% taking and what was the average score? A 581 average math score. Okay? So you've got a value for percent taking, and you have a value for the average SAT math score. So how do I start making the scatter plot? We just picked one state, right? They just picked Colorado to show you what's going on. The point gets fixed by a value for the X and a value for the Y, right? So I've got 14% taking, which is right about there. What was the average score? 581, which is about there. That little dot represents Colorado. I mean, all you see is in these little dots. That's it, right? You don't see any individual's name. You read the values off by giving me an X and a Y. Again, what I see is that point is fixed by a 14 and a 581. That is your X, that is your Y. That's a value for percent taking. That's a value for the Colorado's average SAT math score. Now, you got to do this for all 50 states. In case you don't realize it, this is worse than making a histogram by hand. Right? Because every one of them, I got to put a little dot. I got to find out what was the percent taking for that state, what was the mean score, over, up, little dot. So if I looked here at figure 4.1 on page 104, I'm assuming there's either 50 or 51 dots. If they threw in the District of Columbia, there's 51. Okay? Here's what I would like to do. Look, you folks, this is our end of our fourth week together, right? Yeah? I mean, you got to know what I'm going to do. Hell, I can stand here for the next hour. We can put them 50 dots on there. We ain't going to do that. So I'm going to find this file, and remind me I'm in chapter 4 when I get over here. I'm assuming this is called what here? Math SAT? That was the file here? Remember, it's in the margin. It's Math SAT? Yeah. So all this is, you know, you got the 50 states listed. Let's see if they put in the D.C. They must have, because there's 51. Yeah, they put in D.C. So there's 51 here, right? The 50 states in D.C. And for each one of your individuals, the first column there, you had the percent taking the SAT, and you had the Math SAT, average state Math SAT score, right? There's my data. So if I want to make a scatter plot, I go to Graph. Scatterplot's the first one. Now, I got all kinds of choices here. I got simple, I got with groups, I got with something about putting a line on here. For right now, let's just stick with the simple one, right? I just want one that looks like what's in the book here. And if I click OK, there's always a window that opens up when it wants to know where'd you put things. Now, here's the thing to be careful about. You see that little box? You see where it says the Y variable and it says the X variable? It's asking you for the Y first, right? It's asking you, in this case, what is your response variable? And remember, that was the Math SAT score. You understand if you get these backwards, the graph is flip-flopped. That won't go over good. And then the X, they asked you for that next, and that was the percent taking the SAT. And at this point, I don't screw with anything like changing this or changing that. I'm good, right? So now if I click OK, that looks like my graph in the book, right? That's how they did that. One more warning. It asks you for your Y first, and then it asks you for the X. You notice it's got the percent taking. Down there is the X. That's your explanatory. It's got your Math SAT score going up the Y. That's your response. That's our guy. That's how we do that. Okay? Now, there's one other thing I want to point out to you. I already have, but I'm going to say a little more to you. On the bottom of page 104, there's a box there that says Scatterplot. I want to warn you about this one more time. It says, a scatterplot shows the relationship between two quantitative variables measured on the same individuals. We've already talked about all that. Okay? The values of one variable appear on the horizontal. The values of the other appear on the vertical. Each individual in the data appears as a point in the plot fixed by both variables, right? You got an X, you got a Y, and you fixed the little dot there, correct? That's what it means. Every little dot is an individual. The only way you would have less dots than you have individuals, if you had two individuals in your data set that had the exact same X, the exact same Y, you'd get one dot for both of them, agreed? That's the only way. If not, the number of dots match the number of individuals, unless you got somebody that's the same on both of them. It says always plot the explanatory variable on the X. No options here. The explanatory variable always goes on the X. That means the response always goes on the Y. If there is no explanatory and response distinction, in other words, you just have two variables, and you're interested if they're related or not, put one on the X and one on the Y, nobody cares. Now, I'm going to be honest with you. Most of the time when we do this, 99% of the time, one variable is going to be the explanatory and the other is going to be the response because we're thinking of one of two things. And I'm reviewing with you. I'm thinking one variable explains or influences the other, or I want to use one variable to predict the other. So one's going to be the explainer and one's going to be the response. But if you get two variables and you just look at the relationship, put one on the x, one on the y, done. Okay? Now, here's what I wanted to do before I start interpreting. Right? I mean, that's supposed to display the relationship, but remember, I'm supposed to talk about an overall pattern, striking deviations. I mean, what kind of things do we pick out to talk about with the scatter plot? Do you remember when you look at a histogram, we like to talk about the number of peaks, we like to talk about the shape, right? We like to talk about center and spread. That doesn't fly with a scatter plot. We like to talk about three things, and we're going to get to those in a moment, okay? Here's what I want to do. You see 4.5? I'm on page 105. I want to get another problem up here, okay? It says, airlines have increasingly outsourced the maintenance of their planes to other companies. A concern voiced by critics is that the maintenance may be less carefully done, so the outsourcing creates a safety hazard. In addition, flight delays are often due to maintenance problems, so one might look at government data on percent of major maintenance outsourced and percent of flights delayed blamed on the airline to determine if these concerns are justified. You got two things here, right? You got the percent of work they outsource, the maintenance they outsource, and the percent of their flights that is delayed. Okay? It says, this was done, and data from 2005 and 2006 appeared to justify the concerns of the critics. Translation, what happened with the airlines in 2005 and 2006 is the higher the percentage of maintenance, the higher percentage of delays. Yeah? That was, what is that? That's 10 years ago. Yeah? So what it says is, this was done, and data from 2005, 2006 appeared to justify that. Do more recent data still support the concerns of the critics? Here are the data from 2012, and what is there? There's 2, 4, 6, 8. There's 9 airlines they have data on. They got two variables measured on them. They've got the percent of outsourced maintenance and the percent of flights that are delayed. Everybody understand that, right? So you got 9 individuals, you got two variables here. Now, it says, make a scatter plot that shows the relation between delays and outsourcing. Now, do we think one explains or influences the other here? They never told me, right? They didn't tell me. Do we think one helps explain or influences the other? I got a feeling that the way this whole problem reads here is that the percent of outsourced maintenance helps influence or explains the percent of delayed flights, right? So, let's make a scatter plot. This one here is airline. I want to make a scatter plot, right? Simple one. What do I want my Y to be? I think that's the percent of delayed flights, right? I think that should be the response. I think that's what's being influenced here. And I want to do the percent of outsourced maintenance as my explanatory variable. Okay? I'm assuming there's 9 dots on there. Each one of the airlines. Yeah? Now, here's my question. Well, here's the question that's in the book. Do more recent data still support the concerns of the critics? Here are the data from 2012. Do they? Remember before what the problem was? What I just told you about 2005 and 2006? The critics were upset because the higher the percentage of outsourced maintenance, the higher the percentage of delays. Are we still seeing that? I don't think so. I think they fixed their problem. Look at that one airline that has almost 80% outsourced. They only got like 5% delays, right? You see how the points are going from the upper left down this way? Yeah? As you increase the value of one variable, what are you doing to the value of the other? You're actually decreasing it, right? From upper left down the lower. It's not perfect, right? But it's going this way. As you increase the outsourced percentage maintenance, you are decreasing the percent of delays. Now, hell, that's just the opposite of what you saw in 2005 and 2006. Let me ask you this. I mean, I know we just started with all this stuff. If I gave you a scatter plot of the 2005-2006 data, what do you think it looks like? You think it's going this way? As I increase the outsourced percentage, I increase the percent. That's what the critics were mad about. This one's just the opposite, right? So we don't have that problem now. The airlines must have fixed their problem. Okay? Now, my little hand moves, they have names. Okay? So we got to talk about interpreting a scatterplot. What do you see? Right? You still got to tell me that here. So when I think about interpreting a scatterplot, all right. Now, there's nothing special here. There's a little box that's going to tell you this. I like to do it like this. I'm going to break it up into two pieces, the overall pattern and then the striking deviations. So I'm going to give you like a number 1 here, and somebody asked you to tell me about the overall pattern in a scatter plot. You're going to tell me 3 things. Okay? You're going to tell me direction. I'm going to give you some options here. You're going to give me form. We're going to have a favorite form. And then you're going to tell me strength. Remember before it was shape, center, and spread. Now it's direction, form, and strength with a scatter plot, looking at the relationship between 2 quantitative variables. And then the second one is when you want to talk about striking deviations. What did we call striking deviations with a histogram? What did we call individual observations that didn't fit the overall pattern that we saw? Or let me put it to you the way I actually talked about it. What the hell did we call those guys that were stuck way out in the tails? Those were outliers. That's how they didn't fit the overall pattern before, right? So here when we're talking about striking deviations, they're still going to be called outliers. And it's still the same definition. They don't fit the overall pattern. They're out by themselves. Now, here's the thing. We're going to have a lot to say about this. Direction, form, and strength. I will have more to say to you about outliers in Chapter 5. Okay, these ones that don't fit this overall form. Now, here's what I want to do. Okay? I'm going to come back here. I don't really want to mess with that guy. I want to mess with the one that was in the book here. I want that scatter plot again. Remember, simple one, what was it, math, SAT, percent taking. I kind of want to look at this guy here. And, I mean, we can all see it here. I know everybody can see it. So, when I'm looking at that example, and I'm going to label this example 4.3, or the book does 4.4. Okay? I want to talk to you about direction, form, strength. The direction now I'm going to give you my interpretation of direction here. When I'm looking at this, does everybody see how the points look like they go from the kind of the upper left to the lower right? Yeah? Right, they're kind of following this way. Okay? So that's the first thing I'm going to write. It looks like an upper left to lower right. Everybody agree? Now, that has a name for it. Our book has a name for when we see this idea of this upper left to lower right. It's called a negative association. A negative relationship. Look, I'm still on the direction. I looked at it, hell, I saw upper left to lower right. Okay? What I see is, I got to keep referring you back. You know, a histogram, when you tell me it was skewed to the right, skewed to the left, are roughly symmetric, right? That's what you see in the histogram. And then you actually told me, you described the distribution by telling me what that meant, yes? Same thing here. You tell me that you're looking at your scatter plot and you see the points from upper left to lower right. You're going to tell me it's a negative association. But then you've got to tell me what that means in terms of the two variables we're looking at. Now, I'm going to go back here and look at it one more time. Does everybody see that as I increase the percent taking the SAT, what happens to the state's mean math score? Does it decrease? Right? So I'm thinking about increasing the percent taking. Does that decrease the mean math score? We're going this way, right? As the percent taking increases, the state's mean math score decreases, right? Would it let me write on this? Nope. Okay. So I'm going to put it to you in language back here. In the context of the problem with the variables. As the percent taking increases, the state average SAT math score decreases. Why is that? No thoughts? Pardon me? Yeah. Do you understand what he's telling me is we have a larger group participating, right? You understand the states that have a high SAT math score, those were select people taking that test, right? You understand as the percent increases, that's the state where everybody and their brother's taking the SAT test? Anytime I have a select group doing something versus everybody doing something, the select group's going to have a higher score. It doesn't matter if it's the SAT test, ACT test, any test. Okay? Now, I've done this for you 3 ways. I looked at the picture to see what you were seeing. I gave you the statistician's negative association. And then I've given it to you in the context of the problem. We increased the explanatory variable, we decreased the response variable, right? I gave that to you right there in general terms. Now, when I think about the form, okay, the book is going to tell you the form is that you have 2 clusters. Now, since it won't let me write on mine, it looks like this. And what I see is there's like one here, and there's one over there. Yeah? I see 2 clusters here. I see the states that have a low percent taking, then I have a set of states that looks like they have a high percent taking, right? You understand, if I was going to get real excited here, I'd tell you these are the seems reasonable, right? Now, there might be somebody mixed in between the two, but the ones that have a low percent taking, those are more likely to be the ACT states. The high percent taking, that's the SAT states. So I'm seeing these 2 clusters, right? I actually want to read that part to you here. It says, the form of the relationship is roughly a straight line with a slight curve to the right as it moves down. What is more, most states fall into 2 distinct clusters. Now, I got to do this to you. When they're saying a straight line, now look, you know I'm a math guy, right? They're telling me it's a straight line with a curve. Me being the math guy I am, a straight line's a straight line and a curve is a curve. But here's what they mean. Right? I drew you in a straight line that has a slight curve in it. Look, here's the thing. We're always interested in a particular form. right? So we're always interested in this straight line form. That's going to be our favorite here. You know how in Chapter 3 our favorite density curves are normal? Here our favorite forms are going to be straight lines. So I have a line with a slight, I don't know if it's slight or not, with a curve. Right, it came down and did that. Now, we're going to be mostly interested in no curves. We're going to be interested in straight lines before this is all said and done. In other words, what I'm telling you is, it's telling me the form. They see two clusters, and then they see this line with this slight curve. Our favorite form is going to be a linear form, something that looks like it could be a line. All right, that's going to be the one we deal with most here. Now, my direction was a negative association, right? Upper left to lower right. My form here is, to be honest with you, I see the two clusters better than I see the line with the curve. Okay? But they're always, every time we do anything in this class with a scatter plot, we're always interested in, do we see this form being linear? Do we see a line in the data? That's the reason they throw that in, a line with a curve in it. Okay? Now, when I talk about strength, what we're asking you all is how close, at this point, just looking at it, how close do the points follow the form? Think about the two clusters. The tighter they are, the stronger that form is, right? The more spread out they are, the weaker that form is. I see that curve with a line in it. The closer they follow that line, the stronger it is. The more spread out they are, the weaker it is. And so, if you're going to force me to throw something on here about this guy. Okay, I see your clusters. Hell, I can even see your line with a slight curve, right? If I can see it, then things are getting fairly good here, right, close to the form. So when I have to hedge my bets in this class, especially with stuff like that, I'll throw the word moderately out there at you. Oh, it's moderately strong. Can we see the clusters? Yeah. Can we see the line with the curve? Yeah. I'm going for moderately strong. I didn't tell you it was strong. I didn't tell you it was weak. I'm saying, I can see it. At this point, please, if you had told me like it was strong, moderately strong, halfway strong, whatever word you want, I mean, I would have been good. You can see it, right? You're not going to get counted wrong for that. Okay? Look. I'm going to do better about this in hopefully today, if not on Tuesday. And this one, I'm going to do better with that. We're going to have a calculation. Looking at the form and the strength is like trying to eyeball the center and the spread out of a histogram. Right? And then eventually we calculated it, yes? Same thing here. We're going to have a calculation that tells me about the form. We're going to have a calculation that tells me about the strength. So at this point, I mean, that's like the best I can do. Yeah, you're moderately strong. I see two clusters. I see a line with a curve in it. Okay? Now, on the top of page 107, I like to draw pictures at this point of a negative association. Right? Remember, this was a particular direction we just saw. I would like to draw one, so this is what we're looking for. That's your negative association. Upper left to lower right. Hey, what's your form here? Anybody see the line now? Yeah, you do. Those are the only ones I know how to draw, ones that look linear. Right? Now, here's what I'm going to do. As you increase the value of that variable, you decrease the value of that variable. We already had that talk, right? So you're increasing the value of the variable on the x-axis. You are decreasing the value of the variable that's on your y, right? That's a negative association. That's what it looks like in the scatter plot because that's what it says. And I'm on page 107. Two variables are negatively associated. There's a negative relationship between them when above average values of one tend to accompany above average values of the other. Here's what they mean. You understand that that's below average values of this one, right? They go with above average values of that one. And vice versa is, here is above average values and it's going with below average values. What that means is when you increase the one on the x, you're decreasing the one on the y. Okay? So my little chunks there are supposed to tell you how they match up. Right? If you have below average values of the variable on the x, then you have above average values of the variable on the y. If you have above average values of the variable on the x, you have below average values of the one on the y. Now, you do understand if there's a negative association here, there's going to be a positive association. So the positive association looks like this. And then we'll have a little talk about what's going on there. Now you're from lower left to upper right. When you increase here, you increase there. So if you increase the value of the variable on the x, you increase the value of the variable on the y. Just the opposite. And then the book's going to give you this in terms of above average values and below average values. And all they're going to tell you is, this is below average values of the variable on the x, and they go with below average values here. This is above average values here. It's above average values there. They go together. Below and below, above and above. The other one is just the opposite. So I got three things going on here that I want you to know. I want you to know what it looks like in the scatter plot. Upper left to lower right, negative association. Lower left to upper right, positive association. If you see a negative association, that means when you increase the value of the variable on the x, you decrease the value of the variable on the y. When you see a positive association, that means when you increase the value of the variable on the x, you've increased the value of the variable on the y. And then this, if it's a negative association, below average, above average. Above average, below average. Positive association, below, below, and above. That's what my pictures are trying to tell you here. That way I don't have to remember all the words and stuff. Now, I looked all over the place for some good problems here for this. And the best one I can come up with is this one in example 4.5 that we can see, okay, here's what we're looking at. All right? So when I look at example 4.5, it's something about the manatee. It says the manatees are large, gentle, slow-moving creatures found along the coast of Florida. Many manatees are injured or killed by boats. Table 4.1, which is on page 107, contains data on the number of boats registered in Florida in thousands and the number of manatees killed by boats for the years between 1977 and 2013. So, look, your individuals here are the years from 1977 to 2013. And for each one of the years, you had two things measured on them. The number of boats registered in thousands of boats, and then the number of manatees that were killed by boats. Okay? Your two variables here are the number of boats registered and the number of manatees that are killed. It says, examine the relationship. Is it plausible that restricting the number of boats would help protect manatees? Now, let me ask you this. I'm not going to read the rest of this to you. Do we think that one helps explain or influence the other? I'm pretty sure that the number of boats registered helps explain the number of manatees killed. Or at least that's what we're interested in. I don't know if it does, but that's what we're interested in. And so what I'm trying to tell you is this needs to be my explanatory variable. And this needs to be your... You understand why that's a concern to me? This has got to be your x, and that's got to be your y then, right? Now, what I would like to do is I would like to make the scatter plot for us. All right? So if I'm going to make the scatter plot for us, I'm assuming the title here is manatees. Huh? It doesn't have one. Oh, we're going to have to use theirs then because I'm not typing it in. Okay? So, when I look at the scatter plot, right? And your scatter plot is figure 4.2. The dude puts the same file in the thing there 6 times because the problem gets used over again, but he can't put that one in. Figure 4.2 is the scatter plot. Now, if I ask you about the direction here, does everybody see lower left, upper right? Everybody agree? What does that call for us? You don't tell, look, please don't walk out of this class and tell somebody it's lower left to upper right. You're going to tell them, oh, I see a positive association. Right? I see that lower left to upper right. The other thing I see is, what does that mean? I know that's the definition that's in the book. What's a positive association means? It means as the number of boats registered increases, the number of manatees killed increases. Right? The two variables increase together. So the direction, we looked at it, oh, that's a positive association. Well, what that means to us is that the number of boats registered increases, the number of manatees killed increases. So I got a question for you. Look, there's still a form and a strength, right? The question asked us is, examine the relationship. Is it plausible that restricting the number of boats would help protect manatees? Yes or no? See, me writing that last line there, me going past the point of just telling you you're seeing a positive association, I'm telling you what the relationship is. I'm telling you as the number of boats registered increases, then the number of manatees killed is going to increase. I'm telling you about the relationship. The direction tells you about the relationship. Okay? So the answer to that question is, yeah, it looks like if there were fewer boats, there would be less manatees killed. Yep. Now, what's the form here? We always got to do the 3. The form. No, I'm not going to give you no clusters. I'm not going to give you no line with a curve. That's linear. I see a line there. If you give me a thick enough magic marker, I draw a line, go through all the points, right? Everybody see it? Just draw it. Yep, that's linear form. That's our favorite. Now, what about the strength here? I won't be wishy-washy here with you. That's strong. Because I can see the points falling. They're not going to follow a line exact, but you can see those lines. Those points follow that line right there. That's a strong linear relationship. Now, the way somebody would tell you this is you'd be looking at the relationship between number of boats registered and the number of manatees killed. You would tell them this. I see a strong, positive, linear relationship. Strong, positive, linear relationship. Strength. Direction. Form. Yeah. You just told me everything about it. Anything we're missing is outliers. We're going to talk about that later. All right? You told me the direction, the form, and the strength by that little statement we did each little piece. And again, we're not too wishy-washy about the direction, right? I mean, that was definitely a positive association. Actually, the form there was really good, and that was actually very strong. Okay? Now, I want to ask you a question. I got problem 4.7 on the bottom of page 108. Outsourcing by airlines. Does your plot for exercise 4.5 show a positive, negative, or no association between maintenance outsourcing and delays caused by the airline? If it shows an association, is the association very strong? Are there any outliers? Well, I mean, look, I wanted to say negative association to you when we made it, but we didn't know what that meant. Right? So I want to make the graph again just to show it to you. Delay is the Y, outsource is the X. Anybody see a negative association? Now, things aren't perfect here, right? This is real life data. Do we see like we're going that direction now? Right? I see a little negative association there. What's the form? How linear does it look to you folks? I need a real thick magic marker this time. But, you know, you force me, give me a thick magic marker. Let's do the last thing. How strong is it? No. I can see a little bit of a negative association. If you force me, I might tell you I see something linear. But whatever I'm telling you here ain't very strong, is it? No. Okay? So that's what they were asking you to do there. And then, what about 4.8? Does fast driving waste fuel? How does the fuel consumption of a car change as its speed increases? Oh, kind of an interesting question. Here are the data for a British Ford Escort. Really? Speed is measured in kilometers per hour, and fuel consumption is measured in liters of gasoline used per 100 kilometers traveled. So you've got two different variables, right? You've got the speed in kilometers per hour, and you've got the fuel consumption per 100 kilometers traveled, right, for a British Ford Escort. Yep. So it says make a scatter plot. Obviously, you got two quantitative variables. Our first to do is make the graph. Do you think one's the explanatory and the other's response? Anybody got any thoughts? So if I look at this 4.8, I believe that I have two variables. One is speed and the other one is fuel. I'm thinking that this is your explanatory. This is your response. For some reason, I got a feeling that the speed that you travel will have an influence or explain how much fuel you'll consume. Okay? It says make a scatter plot, which is explanatory. Describe the form of the relationship. It is not linear. Explain why the form of the relationship makes sense. Let's make the relationship. Let's make the scatter plot. We're going to make the scatter plot. Simple one still. This time I think fuel is the Y. The speed is the X, right? I thought that. Come on. Uh-oh. Once we have a little chat about this, that's not really a shocker. Now, it says, we made the scatter plot. Speed was the explanatory, fuel was the response up to Y. It says Describe the form of the relationship. Is that linear? That's like a perfect curve, right? I can't use that word here. That was a curve, right? Yeah? It says it's not linear. Explain why the form of the relationship makes sense. It's kind of weird, right? You get the best gas mileage when you're going slow or you're going very fast. Somewhere around 60 to 80, 40 to 80, that's when you have the lowest. That's when you have the lowest miles per gallon, right? It kind of makes sense. Okay? It says, it does not make sense to describe the variables as either positively associated or negatively associated. Do you see going from upper left to lower right or from lower left to upper right? We don't talk about that direction here. And then it says, is the relationship reasonably strong or quite weak? Oh no, give me a pencil. I'll draw my little curve right through there, right? That's as strong as it gets. Now, what I'd like to do is this. That example, what I see is I'm going to do just like I do all the rest of them. Direction. No. Form. Curve. Strength. Very strong. I got to go back to this just for a second, right? And you're definitely right. My friend here told me that you actually see parabolic, but we'll settle for curve, okay? The odd thing is like when is the highest fuel consumption? Or let's do it like this. This is like miles per gallon, right? Kilometers per gallon, right? Miles per gallon? Liters per kilometers, right? It's British. When's the lowest? In other words, when are you using the most fuel? At what kilometers per hour is that? 60? Everybody see that? And then from 40 to 80, that's when you're using the most? Or the least, sorry. The least? Let me read that again. Speed is measured in kilometers per hour, and fuel consumption is measured in liters of gasoline used per 100 kilometers. Oh, I take everything back I said. No, it's still curved. There's still no association. It's still very strong. But when are we using the least amount of fuel? When we're going between 60 and 40 and 80. The other times you're using, it's fuel consumption, right? Yeah. I apologize. Read it wrong. Okay? So the ends are when you're using the most. In the middle here is when you're using the least. Think about what our speed limits are. Yeah, I understand it's kilometers, ours is miles per hour. Think about what our speed limits are, right? Okay. I got 648. The last thing I want to do is this. All right? And then that will take us and finish us with scatterplots. And then we're going to come back, remember, with scatterplots and correlation. The last thought here is this, and I'll have to show you this on Tuesday. To add a categorical variable to a scatterplot remember, scatterplot's showing you two quantitative variables. To add a categorical variable, in other words, you've got different groups here, you change symbol or color. In other words, you've got a categorical variable, right? It has different categories. Give each category, each group a different symbol, or give each one a different color, and then you can see the different categories, the different groups on your scatter plot. And we'll do one of those on Tuesday. Y'all be careful going to the house. Don't forget my homework problems. And get your homework problems back. I got those to get back to you.